Hello, everyone. Welcome to attend the AsiaGraphics webinar. I'm Lin Gao, the second chair of this webinar tonight. And today we invite two speakers. The first speaker is UK Indo. His talk is exploring WoW with a single image. And the second speaker is Yuken Lai. His talk is about face video generation and editing. Let me introduce the first speaker. The first speaker, UK Indo, is an assistant professor in University of Tsukuba. Previously, he worked as a researcher at the NTT Laboratory. He received his BS, MS, and PhD degree in engineering from University of Tsukuba. His research topics center on image synthesis, image editing, data mining, and machine learning. He is currently interested in applying machine learning to explore exciting image editing applications. And now let's invite the first speaker to the UK Indo to give the talk. Hi.
Hi. Can I share my screen?
Yeah.
Okay. Could you see my slide?
All right, I think it's good.
Okay, thank you. Okay, thank you for the introduction. And it's great pleasure and my honor to have this opportunity. Today, I'm going to talk about our works for image and video synthesis with single images. So yeah, the title is Exploring WoW with Single Images. So first, let me start my presentation with self-introduction. My name is Yuki Endo, and I am an assistant professor in University of Tsukuba in Japan. I also graduated from this university from bachelor to PhD courses. My supervisor was Professor Kanamori, and I am working with him now. He also gave me advice about preparing this talk, and I would like to thank him here. My research theme when I was a student was image editing, and I wanted to do research that makes people say, wow, only with single images, as I will introduce later. Also, previously, I worked as a researcher in NTT Corporation, which is a telephone company in Japan, but conduct a broad range of research and development. I was engaged on research on data mining there. So I would like to briefly introduce our previous research projects. When I was a bachelor and master student, I worked on projects using single images as input, aimed at synthesizing real-world phenomena such as water flow stain, weathering, and wavy reflection. And after that, in NTT laboratories, I conducted research on positional data mining for live logging services. So these projects are different from computer graphics. For example, as you can see in the right, here, we want to estimate transportation modes from GPS trajectories. In this case, we used deep neural networks to find effective feature representations from input trajectories. And we also developed a method for destination prediction. This work predicts a user's destination from partial trajectories using recurrent neural networks. Okay. Since around I became an assistant professor, we started research on image synthesis and editing using deep learning that I learned from data mining project. However, applying general deep neural networks like UNet to specific tasks did not always work due to the problem complexity. So we needed to carefully incorporate respective domain knowledge into models. These three projects are the cases. For example, single image HDR inference, human image relighting, and animating landscape images. Also, we developed image editing techniques with user interaction, such as edit propagation, semantic image synthesis, and GAN image manipulation. Today, I introduce mainly these three topics. The first project is deep reverse tone mapping, and this work was published at SIGGRAPH Asia 2017. First, I would like to start with background. As you may know, commodity cameras can capture only limited luminance range. For example, with changing camera exposure values, we can take photographs with varying brightness. With low exposure, we can capture the brightness of the sky, but the leaves are blacked out like this. In contrast, with high exposure, the leaves can be captured, but the sky is saturated. As we can see, low dynamic range or LDR images cannot capture the such rich tone variations in the real world. In contrast, high dynamic range or HDR images can capture rich tone variations. To generate an HDR image, photographers conventionally take multiple LDR images with varying exposures and merge them. Such LDR images are called bracketed images. Also, special devices for capturing HDR images or videos are under active development. Unfortunately, such devices are still unaffordable, and both approaches cannot be applied to the enormous images available on the web. So our goal is to simply infer an HDR image from a single LDR image. This problem is challenging and ill-posed because we must compensate lost data caused by under or overexposure and color quantization. So now I review some related work. Single image techniques for reconstructing HDR images are called reverse tone mapping. Existing reverse tone mapping operators employ heuristics and optionally use manual intervention, but it cannot compensate missing information of clipped regions sufficiently. To enrich the clipped regions, example-based techniques transfer texture details from appropriately exposed patches. The disadvantage is that we must specify reference images and regions manually. So in this work, we proposed the first reverse tone mapping method based on deep learning, which can handle both try to handle both overexposed and underexposed pixels. Here is an example pair of an LDR input and our HDR output. Let us see the difference in detail. So this is the LDR input. And as you can see, the woods are almost black. Indeed, the most pixels on woods are underexposed. Here, we visualize the underexposed pixels by painting them in red or magenta. If we increase exposure, we can see the underexposed pixels remain black or become noisy. This is our HDR output with tone mapping. As you see, the underexposed pixels now have plausible colors. To realize deep learning-based inference, a straightforward way would be a direct end-to-end learning. So we actually tried this using a network similar to pix-to-pix. However, we could not plausibly reproduce even training data, especially in dark regions. This is probably due to instability of training, slight variations of pixel values, and the lack of sufficient training data in order to learn large tone variations. So instead of the direct approach, we adopt an indirect approach for learning less variations. We first learn a series of bracketed LDR images with increased and decreased exposures and infer bracketed images. We then reconstruct an HDR image by merging the bracketed LDR images using conventional algorithms. So in summary, our contributions are mainly twofold. First, we propose the first deep learning-based framework for automatically inferring an HDR image from a single LDR input. Second, we propose a network model designed to infer bracketed images with increased and decreased exposures, as well as how to generate its training data. This is the overview of our framework, and the flow is basically decomposed into 3 phases. The first phase is to create training data. To learn exposure changes, we first create the bracketed LDR images from HDR databases by simulating cameras. Here we use multiple camera response functions in the database to get various LDR images. The second phase is to train our networks, and we train 2 networks using the bracketed LDR images. Finally, we infer an HDR image, and from a single input LDR image, the trained models compute LDR images with varying exposures. The final HDR image is then generated from these bracketed LDR images. Now I introduce the architecture of our network. Here, the unique point is that we use 3D decomposition decoder and connect it to the 2D convolution encoder using skip connections. Our input is a single RGB image, and our outputs are multiple RGB images. So from a 3D tensor, our network outputs as 4D tensor. For more details, please refer to our paper. In the training phase, we train 2 models of the same architecture. Namely, the up exposure model is for increasing exposure, and the down exposure model is for decreasing exposure. We train them separately, assuming that our up and down exposure networks learn different features. For example, in the training of the up exposure model, it learns to predict brighter LDR images in this direction. And for the down exposure model, we train it so that it predicts darker LDR images in this reverse direction. Next, I explain a little more detail on the training of our up exposure model. Given the input image, the network outputs are for the tensor like this, and we train the network by minimizing the differences between the network output and ground truth brighter bracketed images. We would like to utilize as many images as possible so that the network can learn relative exposure change. So we repeatedly compute losses by shifting the input and ground truth images like this and this. This is the loss function for the up exposure model. And we measure the differences between ground truth and network output by L1 norm. Here, the zero tensor padding and masking are used to adjust the length of the input and output when we shift the input. The down exposure model is also optimized similarly. So we conducted a quantitative evaluation by comparing differences between inferred HDR images and ground truth. As an evaluation metric, we use the Q-score of HDR VDP2, which can compute visibility difference based on human perception. We computed the Q-scores averaged over about 700 scenes. As we can see in the right graph, our results record best scores, and here our sRGB is a result learned only with a single sRGB camera response function. So this indicates that learning multiple CR camera response functions is helpful. Here are some qualitative comparisons with the scene, and if we observe these regions, we can see the differences like this. Compared to others, our method reproduces the most plausible colors. This is another set of results. And here, the sky region is largely saturated. As you can see, the sky region remains empty in other results, but in our results, cloud-like patterns appear. Okay. However, we think our results have several artifacts and they are still not subjectively perfect. Actually, recently, Henge et al. Pointed out discrepancy between objective and subjective quality scores in some single image HDR reconstruction methods. They also proposed a new evaluation protocol more correlated with subjective quality. So although our results have room for improvement, we hope that our first effort for this task using deep learning stimulates the future work. Next, I will introduce this project. This project is animating landscape, which is a project for a single image video synthesis. Okay, and to animate a single still image, a simple solution is to use commercial software such as Adobe After Effects. However, it requires daunting manual operations. Let's see an example. This video shows how to create an animation from a single image. And as you see, the artist has to manually specify object areas, such as the water surface and sky, as well as motion direction. And user also needs to add some lighting effects, something like that. So our goal is animating landscape, and we aim to automatically synthesize a video from a single landscape image. Our main targets are time-lapse videos, especially with skies and waters. The prior work of video synthesis can be divided into two categories. The first category is the example-based approach. For example, this work generated fluid motion in a single image by synthesizing flows in reference video database. Also, some methods reproduce time-varying appearance, such as day-to-night transition, by a fine color mapping induced from a reference time-lapse video. Another category, the learning-based approach, does not require reference videos. For example, Vondrik et al. Showed impressive results by using 3D convolutional neural networks. Then Lee et al. Generated more photorealistic videos by learning flow fields in a supervised manner. This method focused on motion, whereas some methods focus on color appearance. As you can see, style transfer method can reproduce color transitions like this. Now we summarize the problem of our prior work. On one hand, the example-based approach requires appropriate reference videos. Also, the cost for video synthesis is high, for example, due to optimization. On the other hand, the learning-based approach does not require reference videos, but the results are monotonous and short-term animations. Additionally, the quality of generated videos is still low, and that is low resolution and flickering artifacts. So with these problems in mind, we would like to develop a video generation method with following advantages. First, we want to predict videos at low cost without reference videos. Second, resultant animations should be diverse in terms of moving clouds, changing sky color, and rippling waters, and so on. Finally, their quality must be high, that is high resolution and without flickering. To this end, our key idea comes from an observation that motion and appearance in time-lapse videos have different time scale and spatial frequencies. In particular, motion of clouds and waters changes rapidly, while appearance of the sky changes slowly with smooth spatial variation. Because learning both factors in a single model is not straightforward, we train two models separately with control mechanisms using latent codes. As network architectures for learning motion and appearance, we adopt 2D CNNs in contrast to 3D CNNs for the previous work. Using 2D CNNs, we are not limited by the number of output frames thanks to recurrent feeding and latent space interpolation I explained later. Also, we predict output frames indirectly. Most of the previous work predicts output frames directly, but the pixel-wise inference of high-resolution images is difficult and suffers from overfitting. Instead, our method learns regularized and smooth intermediate maps in a self-supervised manner to reduce overfitting. Now I explain the details of our video synthesis pipeline. From this input image, our motion predictor generates a backward flow sequence. Using these backward flows, we apply warping to the input image to generate animated frames. We next make the warped frames looped if needed, and then our appearance predictor computes color transfer maps for each frame. We obtain final output videos by applying color transfer to each frame. We also introduce latent codes to handle future uncertainty. Now I explain the details of inference with each predictor and their training. In the inference phase, our motion predictor infers a single backward flow field. Because prediction holds future uncertainty, we introduce an environment factor as a latent code. With a different latent code, we get a different output flow like this. And then we warp the input image using the flow and obtain the output image. To predict the next frame, we recurrently feed predicted frames to the network and obtain multiple flow fields. We can reconstruct sequential output images from the input image and flow sequence. And to train our motion predictor, we use two loss functions. The first one is a pixel-wide L2 loss between the prediction and the ground truth of the next frame. The second one is a weighted total variation loss based on the next frame. This is used to smoothen the backward flows. Also, we need latent codes as input during training. These latent codes are generated by our motion encoder from the backward flows. However, the problem here is that the ground truth flows are not available. So our solution is to reuse the predicted flows for each scene during the training phase like this. Next, I explain the inference process with our appearance predictor. First, our appearance predictor generates color transfer maps, each encoding 3 channel parameters required for color transfer. We can obtain the output image by applying color transfer to the input image. By feeding multiple latent codes, we obtain multiple output images. Here, unlike the recurrent prediction for motion, we feed a latent code sequence to reproduce appearance transitions. If we employ a recurrent prediction used for motion, error accumulates in the RGB color space, and we obtain visually poor results, as you can see in the bottom right. To tackle this, we employ temporal interpolation in a latent space. This makes our approach tolerant to error accumulation and flicker-free. This slide shows training for our appearance predictor. First, we use a content loss to preserve the input image content in the output image. Second, we use a weighted total variation loss to smoothen the color transfer maps according to the input image. Third, we use two losses for transferring the style and the spatial color distribution of the target frame. For more details of our loss functions, please refer to our paper. Finally, our appearance encoder extracts the latent code from the target frame. Each latent code implicitly represents a time factor, such as daytime, evening, or night. Here, we now compare results, and the 3 videos in the top right show that the compared methods generate low resolution and short-term videos. Although Lee et al.'s method predicts optical flows, the quality is low. In contrast, our method can generate high-resolution videos with plausible flows according to the scene structure. Our method can also generate longer-term videos with appearance transitions like this. Here is also a comparison with the attribute manipulation method using deep learning. As you see, the prior work in the middle causes flickering artifacts, while ours on the right is a smooth transition. Here, I explain the limitations of our method. As you can see at the bottom right, in the red circle, very long-term predictions for motion cause unnatural distortions. This is because error accumulates in flow fields by recurrent prediction. Our method is also difficult to generalize to various some outdoor scenes. So after our paper published, various methods for single image video generation have been proposed, such as deep landscape, endless loops, and Aurelian motion fields. These methods can generate more realistic animations for various scenes. As you can see in the bottom figure, the recent technique also allows the user to control fluid directions by annotating the image. Okay, finally, I would like to introduce this project. This project tackled the problem of editing against image layout. And I'm going to present this work at AsiaGraphics next week. So I'd like to start with background. And as you may know, exploring latent space for controlling GANs is a recent hot topic. It's also called latent space navigation, GAN steerability, etc. This technique aims to discover interpretable latent directions in the latent space. For example, as you see in here, we can manipulate age for a human face by moving a latent code along a specific direction. However, existing approaches for latent code exploration have some problems. There are mainly two approaches for this task. The supervised approach uses a classifier that detects attributes such as gender and age. However, its manipulations are limited to predefined attributes and needs training data for classifying attributes. Meanwhile, the unsupervised approach does not require such training data, but struggles to identify latent directions. Also, as you can see, both approaches perform 1D operations using a slider interface. As a result, it's difficult to intuitively control spatial layouts like poses. So our goal is to intuitively control style GAN image layout by annotating an image directly. In the left image, the user specifies a movement direction on a cat body using a mouse. Given such user input, we want to estimate an edited image like this. So our research question is it possible to control latent codes in accordance with user annotations on the image? To this end, we propose a novel latent transformer conditioned on user inputs. This can transform input latent codes into edited latent codes using the user input. The edited latent codes are fed to StyleGANs to obtain edited images like this. However, there remains ambiguity about where the parts move. For example, the 4 feet in the red circle move down with the body. To alleviate this ambiguity, we propose to use anchor points to specify points that should not move. Given anchor points, our latent transformer manipulates the latent codes so that the 4 feet positions do not change as much as possible. Also, specifying anchor points on the ears, we can see that their positions are fixed. Meanwhile, 2D mouse dragging like this cannot handle 3D motion. So we use additional keystrokes to specify 3D motion. Here is an example of zooming out, and here is an example of zooming in. Because our method edits images in the latent space, we can apply other latent code manipulations together, such as style mixing. A latent transformer was recently proposed by Yao et al. It's defined as this equation. Given latent codes, W and the parameter alpha, it moves the latent codes along a direction obtained from a DNA-based function. This figure shows an example of latent code manipulation using a latent transformer for adding glasses. Different from the existing latent transformer, we use user inputs U as additional inputs. Conditioned on U, our latent transformer is defined as this equation. Here, the user input U consists of a set of k motion vectors V and start point P. As you see in here, our latent transformer estimates edited latent codes in accordance with multiple user inputs specified on the images. To design a latent transformer, we first considered using existing architectures. Existing work uses multi-layer perceptron, as shown in the right figure. However, image manipulations are limited to fixed attributes such as glasses and gender. So MLP-based architecture is inappropriate to our problem setting, which uses variable length inputs. To solve this problem, we develop a latent transformer based on transformer encoder-decoder to handle multiple user inputs. This slide shows the architecture of our latent transformer, but I omit the details to explanation due to the time limit. And in this slide, I explain a training pipeline for our latent transformer. In a single iteration of training time, we first generate 2 images randomly using a StyleGAN. To do so, we first sample latent codes from prior and then randomly perturb them. Next, we estimate 3D optical flows using a pre-trained optical flow model. We then subsample the optical flows to reduce computational cost for the transformer encoder-decoder. Finally, we use these obtained flows as pseudo-user inputs for the latent transformer. Here, we minimize the loss function between the perturbed latent codes and latent transformer outputs. This slide shows some of our results, and we can manipulate images in accordance with user inputs. In particular, specifying anchor points prevents some parts from moving with other parts. Okay. This slide shows a comparison with the existing method SEPA. Here, lower left values in the CEPHA results indicate adjusted parameters, namely latent direction ID and editing amount. CEPHA is an unsupervised approach and can find interpretable latent directions, but it needs to identify and tune different parameters and cannot always reproduce results like ours. I also discuss our limitations, and our method sometimes struggles to preserve content in images. For example, the upper left figure shows disappearance of glasses on human face, and in the right figure, extreme user input also causes identity change for a cat. Localized control is also difficult. For example, specifying many anchor points to change the tire size only would change the cart shape globally. This is because training data are created by randomly manipulating latent codes, but this manipulation itself is not completely disentangled. Finally, I want to introduce some exciting concurrent works. Here, P and A in the left figure can extract latent directions for local regions. This can be achieved by semi-non-negative tensor factorization for style GAN feature maps. And blob GAN in the right figure learns to associate different blobs with different entities in a scene. But I cannot play the video here. It can arrange these blobs to capture scene layout. So in the future, I am interested in enabling more fine-grained control for image generative models like this. Finally, I summarized today's talk. I talked about image synthesis and editing applications with single images using deep learning. In this talk, I introduced methods for a single HDR reconstruction and landscape video generation and GAN image layout manipulation. We hope that our insights will facilitate future research by providing novel deep learning solutions to explore WoW with single images. And if you are interested in our projects, please visit our website. Okay, that's all. Thank you for your attention.
Okay, very nice talk. So, is there any question? So I have one question. Professor Indo, I have a question is for the second work, how to obtain the same parameters such as the one parameter input into the motion prediction network. How to obtain the same parameter such as the wind parameter input into the motion prediction network.
Okay, thank you for the question. Wait a moment. Do you mean, sorry, do you mean what is the parameter for motion predictor?
Yes, the wind speed of the parameter of the wind speed, how to estimate or how to input the speed of the wind.
Do you mean this latent code?
Yes.
Okay. Yeah. Our method estimated this latent code parameters used from videos in databases and using encoder. So we use encoder to extract this latent code from videos in the database. That's my answer. Does it answer your question?
Yes. Okay.
Okay.
And I have another question, and a very nice talk, and also very inspired. So the second question that in the third work, I find that the identity had also been changed when editing the face or animal images. It is easy to keep the identity of the face unchanged, just change the pose. I see some examples. The identity of the face has also been changed. It is possible to keep the identity, the ID of the face unchanged. Is it possible to keep?
Thank you. Thank you for the question. Is your question? I can keep identity in, for example, in this in this image. Sorry, do you mean?
Yes. Could you keep the identity? Is there some laws to ensure this? Yes. Is there some loss function to keep the ID unchanged, or there is no loss, but the result could not be changed?
I see. Actually, our method cannot keep identity as I show in this slide. For example, if we move extremely this human face to extremely move, and we will obtain, we cannot keep identity of this person.
Okay, I think that there would be some. This would be some future work maybe. Yeah. Okay. Okay. Thank you, Professor Indo. Very nice talk, and we thank the professor. The nice talk again. Thanks a lot.
Thank you very much. Thank you.
Okay, and now let us invite the second speaker. The second speaker is Professor Yu Kunlai from Cardiff University. And Yu Kunlai received his BS and PhD degree from Tsinghua University. And he had been working on computer graphics, geometry processing, and computer vision for over 15 years, and had published over 100 papers in major international journals. He is also an associate editor for computer graphics forum and the visual computer journal. He was also the conference co-chair of many graphics conference. And now we invite the Professor Yu Kunlai to give the talk face video generation and editing. So is Yu Kun there?
Yeah, thanks for the nice introduction. I'm just trying to share my screen. I think it only allows one person to share, so I can do it now.
I just stop the sharing.
That's right. Hopefully you can see my screen.
Yeah, good.
Okay, so so we all know that face videos are common in many applications. Even if for some videos they are not entirely about faces, you can often see people talking, people as part of the whole environment. So you can argue that face videos are basically everywhere. So in many practical settings, it can be quite difficult or quite expensive to take certain specific face videos. Obviously, if you ask some celebrity to speak or talk about certain things, that can be expensive. Obviously, there are also cases where it can be really difficult to capture for some people in the past. And in practice, even if you have taken some photo, some face videos or videos involving some people talking, if you later find there are some issues and you want to make some changes, that can also be very difficult and time consuming. So in my talk, I basically want to talk about a few of our recent research, trying to basically either generate talking face videos or trying to edit talking face videos. Okay, the first work I'm thinking about is basically if you're given a video of a specific person and also an audio, basically it's like a speech, and how we can actually synthesize an output video that basically has the same identity and appearance as input video, but also has a lips and so on synchronized with the audio, so that it looks like a natural sort of a video that works along with the given audio. So there are some practical challenges. For example, we hope that results can be generated in real time. So in many cases, if we have an audio which can change, and we hope that the generated video can be produced basically at the same time as audio is played. An obvious requirement: results should be free from artifacts. When we do this transfer of video to the new audio, we want the identity to be preserved. I think that's something that was discussed from the previous talk. And when someone is talking, often they have some head motion, as you can see when I'm talking. So how we can actually make sure this kind of natural head motion is retained rather than lost. But we also have the synchronization regarding expression and voice. So there are a few challenges. Now, I have to say that's quite a lot of work in this area. So the question is how we can actually satisfy all these requirements. So I'll focus on some main ideas. Now, one of the things it's quite obvious is this is clearly a multi-domain application. So the input includes some kind of audio signal. The output essentially is a video signal. So how can we actually fuse this multimodal kind of data and input along with audio? There's also a video input as well. So how can we effectively fuse this kind of multimodal input? There are basically two traditional methods. One is we can basically extract some features from the audio, as you can see from the right hand side. I don't know if you can see my pointer, so I'll just do the. Yeah, so basically, as you can see, if you can turn that audio signal into some audio features, and then you need to sort of basically replicate that features to cover everywhere on the image, because image covers some area, and we want to make sure that this kind of features are kind of concatenated with audio signals, concatenated with image features. Then we can use convolutional neural network to deal with this kind of expanded or blended data. The problem with this is when we use, often when you learn this kind of behavior, we often need to have these spatial features aligned. Otherwise, it can be quite tricky to learn. Another approach often done is to extract some facial features, and you can build some like 2D or 3D models based on like a facial landmarks or facial parametric models. Now, the problem with this kind of approaches is obviously relies on the success of extracting these kind of facial features. So these methods can be less robust, and they can also be sometimes can be more time consuming. So what we propose here is an approach where the audio signals is extracted using you can extract some features from the audio signal, and that extracted features are now generated as a dynamic convolutional kernel. So ultimately, when you have a video input, that video input goes through a fully convolutional neural network, and you can generate the designed output. Okay, so by doing so, the video stream, if it goes through the video part, it's just a fully convolutional neural network. The difference here is that for certain layers, the convolutional kernels are not predefined or predefined during the training process. They're actually they're actually generated on the fly given the input audio input. Okay, so audio input going through a neural network to predict the convolutional kernels, which are then applied to certain layers of the video parts. So that's the main idea. Instead of using fixed convolutions, we use dynamic convolutional kernels. And these dynamic convolutional kernels are driven by the audio, and therefore we can actually use that to achieve this multimodal fusion. Okay, so this is the overall pipeline. It's actually quite straightforward. So if this is the audio part, so given the input audio, we go through a pre-trained audio network, and then you can get some audio features. This can go through some fully connecting layer, and then you get this feature which can be reshaped to the size of the kernel of the neural network. And for the video part, it's done frame by frame. Basically, we can just crop one frame, we can get the face part that goes through this. Is essentially it's a fully convolutional neural network with certain layers being having dynamic convolutional kernels. Okay, these are basically just determined by this audio branch. And at the end, we can generate some certain outputs. Now, in order to achieve real-time performance, one thing which is also important is that we want to make sure that the output can be easily blended to the original video to get to the final output. So how do we achieve that? Instead of generating some image output, which still then needs to be seamlessly integrated with the input frame to generate a nice image, we basically generate two outputs. One is called attention mask, which basically describe which pixels need to be modified according to this audio. And we also generate an image like thing called a motion image. Now we call it motion image, but what it really means is that for these pixels which are aligned with attention mask, we want to blend this output with the input frame to generate the output. Okay, so intuitively, the attention mask can be treated as a weight to decide whether the output comes from the input frame or what portion of this output comes from the input frame and what portion come from the motion image. Now, this motion image may look a little bit funny, but that's because actually anything outside of the attention mask doesn't really matter. So only those pixels which have a strong response from the attention mask will actually be effective. Okay, so once we generate this output, what we can do is we can just overlay onto the original image to generate the video we want. Okay, so as I mentioned, the blending process is actually quite straightforward. We can just take so the method basically predicts this attention mask. This alpha is attention mask. So attention mask, we do an element-wise multiplication with the motion image, and then we have the 1 minus alpha with element-wise multiplication with the input image. Yeah, so you can see basically attention mask is treated as used to select which part actually from the output, which what proportion from the motion image, what proportion from the original input image. Okay, by doing so, we can actually avoid the expensive image fusion process, and we can then, once we can get the output, we can just simply overlay onto the original input image without any blending operation, any further blending operation. So by doing so, we can actually achieve real-time performance, 60 FPS. Okay. So the effect of blending, we can see from this simple example. Now we are saying the input is actually a video. Now it doesn't need to be a video. In certain cases, we can just a simple image. We just duplicate this image as many times as we need. And given some audio signal, as you can see, this is a generated mask. And this is the motion image. As mentioned, only those actually matching these attention masks are relevant. The other pixels we can basically ignore. And when we do this blended, when we do the simple linear blending of the motion and the input, and we can actually generate the output, as we can see. Now, basically by doing so, we can guarantee that the output actually has the same head pose as the input. So which means that if we have a natural video with proper head motion, then these will actually be reproduced automatically in the output video. Okay, so these are some examples, some comparisons with existing methods. Now, although there are many methods, you can see that there are also still lots of challenges. Some of the methods actually only focus on the facial area with the faces aligned, and by doing so, you can see we can't easily go back to the original input, and we can't really have the background properly generated. Some other methods, for example, you can see this is another method which is also relatively fast and also can achieve real-time performance. But if you look more closely, the boundary between the generated image and the original image actually has some clear artifacts. If you look more closely, you can see that. So it is actually more complicated a task than you may originally think. I also show some video.
Truth.
2015 was not that laudable. There was lots of shortcoming, but having learned from that experience, we've beefed up the disease control infrastructure and the legal framework, and that has really been put to the full test, and successfully, I must say, this time.
South Korean President Moon Jae-in held a cabinet meeting on Tuesday, and that's where he said that South Korea was in this all-out war against this virus, and he has ordered all his ministries to be on a 24-hour emergency alert. He has ordered all his ministries and government officials to coordinate closely so that they can resolve all the issues that's coming out.
Comparison with state-of-the-arts.
For decades, Americans have been deeply concerned.
As you can see, some methods have been a problem with creating a stable output. Some other method results are quite blurry.
There's more to be done, President Obama said. We remain concerned about Burma's closed political system, its treatment of minorities and holding of political prisoners, and its relationship with North Korea.
In a popular American short story, a young couple, poor but very much in love, frets over what to give each other for Christmas. To buy her husband Jim a chain for his proudest possession, a gold pocket watch.
Entrepreneurs and their business endeavors are the engines of economic growth and job creation, which in turn are the underpinnings of stability and opportunity.
Ablation study.
For many of us who are working in environmental, economic, energy science and technology issues, this is a very exciting day. For many of us who are working in environmental, economic, energy science and technology issues, this is a very exciting day. The administration of President Barack Obama believes that women are crucial to ending conflict and building lasting security. Studies suggest that countries where women are safe and valued by society are more likely to be peaceful.
As you can see in some previous examples, the input are actually a single image, and therefore you wouldn't see any head motion. Now, if the input is a video, that head motion will be retained, and therefore you will probably see them as more natural. But other than that, as you can see, for the same audio, you can easily apply that to different people, and their appearance and identity are well preserved. Okay, so in the previous case, basically we can generate a video based on generate a talking face video based on an input video along with an audio signal. Now, is there any way we can generate something which also isn't like a talking face, but also stylized? Now, these can create some more sort of artistic effects. So instead of generating the audio, the video like before, like normal face video, we can generate we can also generate some stylized version. So this is some example here. Okay, so so instead of generating, so traditional existing method basically focus on two aspects. One is how to generate some images given an input photo. So given a photo, we can generate different styles of like line drawing and so on. And alternatively, you can also generate something like
AsiaGraphics is one of the most highly respected venues.
And you can see, you can also generate something like someone talking, but like a normal video. So the challenge we have here is how can we generate some video driven by an audio signal, but that's highly stylized. Okay, so some examples we want to achieve here is like this.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
So as we can see, we want to make sure that faces, faces are actually changed according to the speech, but also these are also consistently stylized according to specific style we want to achieve. Okay, so there are a few challenges. So we can't really find any previous works to address both problems at the same time. So we consider some alternative baseline approaches. Now, one obvious baseline approach is we can simply just apply some realistic talking face generation methods, and then we follow by some domain transfer methods. Okay, so if we have a method to generate a realistic talking face, and then we apply these kind of say stylization methods frame by frame, we can just generate some results.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
Yeah, as you can see, it sort of works okay, but there are a few issues. So there are some clear interframe discontinuity. Some little bits and pieces come up and then disappear in a quite random way, so which looks a bit messy. Alternatively, we can basically just stylize the first image, and then we can then use a word-based approach like this.
For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
So there's no issue with discontinuity, but here it looks almost like too smooth and then becomes unnatural. So it looks like as if it's a single image being sort of manipulated, being warped or being deformed, rather than some natural movement, as you can see.
Example, we have the word ache. For example, we have the word.
Okay, so what we want to do is we want to generate a talking portrait line drawing of some portrait, some portrait video in a stylized way. Okay, so and given a single face, a photo, and a speech signal. So as mentioned, there are a few challenges, and we want to cope with this. So we want to use some feature warping approach to generate some sort of useful features to allow these stylized results to be generated. And we also want to make sure that we want to cope with make sure we can cope with the geometry changes, and also we want to make sure the results are temporally coherent. So we want to introduce some new ways to measure and penalize incoherent results. Okay, so basically the approach involves two stages, as you can see. For the first stage, essentially we basically use a standard existing methods called make it talk. The first stage, what we want to do is to take a face photo and also an audio sequence, and we use that to generate some landmarks which are aligned with the audio signal. So in order to get the better results, we can directly predict the facial landmarks, but we use basically a blending of two approaches. One is so-called a speaker agnostic branch to get some general displacements, but also some speaker-specific branch to generate some speaker-specific displacement, and we can then blend them to get the final landmarks. Okay, so given a face photo and an audio sequence, the task of this stage is basically to generate a sequence of facial landmarks. And the next stage, which essentially is the focus of our work, is to basically want to transform a face photo along with a sequence of 2D facial landmarks to generate a sequence of stylized images, including some sort of drawings. Okay, so the challenge here is one thing is we need to do simultaneous style transfer and tracking of facial changes. So basically the output is needed to align with the 2D landmarks, but also properly stylized. And we also want to make sure the output is temporally coherent and without sufficient training data, as we can imagine. Okay, so we used a different strategy to cope with these challenges to make sure the results are, what we want to achieve is the style is transferred, the shape is aligned, but also the result is of sufficient quality. So we don't want to generate results that look like just warping images, but also we don't want the result to be entirely frame by frame and therefore lose the natural sort of coherence. Okay, so this part of the approach is actually quite straightforward. We basically use two ideas. One is we need to warp the input. We want to warp the input according to landmarks. So here we have a source landmark, which is a landmarks of the first frame, but also the target landmark which is a landmark from the specific frame we want to generate. So basically we have two sets of landmarks, source and target, and source landmarks actually aligned with the input photo. So in order to generate the result we want, basically we can use an image encoder to extract some image features. These features can be considered as different levels. And then once we have the source landmark and target landmark, we can encode that and work out a flow map from these two sets of landmarks. Then we can apply this kind of feature warping. Instead of applying them to images, we apply them to features at different scales. So we can apply these kind of flow map or flow and feature warping at these different convolutional feature layers, feature outputs. And then we use these to drive manipulate the image frames are combined and going through this transfer module to turn that into a stylized output. Then you have the image decoder to generate the final results. And in order to make sure the results are of high quality, but also videos, we basically used multiple sets of discriminators. The drawing discriminator basically tries to say, okay, try to differentiate high quality and generate the real and generated images from the drawing or from the image perspective. So we basically combine a global discriminator of the whole image, but also local discriminators trying to look at the focus on important facial features, including eyes, nose, and lips. Because these are the important parts to differentiate real and fake images. That's drawing discriminator. We also want to make sure temporal coherence. Therefore, we also have some temporal coherence discriminator. Basically, we want to differentiate real and the fake ones. Now, in reality, how do you actually get proper temporal coherence training data? So it's quite tricky because we don't really have lots of real line drawings. So for line drawing, as an example, we actually have quite an attractive strategy. Basically, what we do is that we take a color portrait film, and basically that's largely made up of this kind of line drawings, and we can extract lines from it. So apart from the color, we can actually extract these lines directly from this kind of film, and we can use that to actually get some pseudo ground truths to help us train this model. Basically, if you take the adjacent frames from this processed film, these are considered as positive case, and for negative case, these can be the ones either generated from the drawings from the method. So these are the negative cases, or these can be non-adjacent frames from the processed portrait film. Okay. So in addition to, basically we have these pseudo ground truths, which are adjacent frames from this process or extracted lines from the portrait film, and also have fake examples, which are either the ones generated from the generated drawings or the ones which come from the non-adjacent frames from that video. So by doing so, we actually have some ground truth or label data, essentially pseudo label data, to help us train this discriminator. Okay, so once we have this, we can actually put them all together. So we have a few losses. I can briefly talk about all these main ideas. We have the adversary loss, which is quite standard at the image level, trying to differentiate real and generated images. We also have a warping-based content loss because the method can generate some output, and we can then apply some warp on top of the output, and then we can basically generate a static line drawing from the input. So that's of high quality. You can warp that static image towards based on the landmark. So therefore, we can actually generate some approximate ground truth. So this is a warped image, and then we can work out the difference between this warped image and the generated image as a way to basically make sure the content is retained. We can also measure some other properties. For example, we can want to make sure the landmarks are properly retained. So for example, for the generated output, we can extract landmark, and we can compare the landmark with the landmark from of the target frame. We can also, in particular, look at the lip contour as well. And in addition to that, we can also want to make sure the output also retains identity as much as possible. And from the other side, we also want to make sure that better, the interframe warping maintains kind of a temporal coherence. So we can basically generate two sets of generate two drawings based on two sets of target landmarks with slight changes. These can be like landmarks from adjacent, extract from adjacent frames. We want to apply because they are similar landmarks. We can apply some warping based on the difference to get an approximation. So basically, we are saying, okay, if two sets of landmarks are quite close, so T1 and T2 are two sets of landmarks. If they're close enough, and the P is the source landmark, then we can basically generate two images and then warp one toward the other, and they should be very close to each other. So the assumption is if the landmarks are close enough, the generation basically can be easily aligned by applying a simple warping on top of one result toward the other. And for temporal examples, as we mentioned, basically we use three different test sources of images to help train the model to ensure temporal coherence. And so when someone is talking now, the foreground face or head can move around, but the background should stay still. So what we do is basically we use a simple approach to extract foreground and generate foreground drawing using the proposed generator. And the background we can simply generate using a static generation stylization method, and we can then blend these two. Okay, so anyway, I can show some of the results here. As we mentioned, we can use different ways to get the training data. That includes some of the artist-drawn line drawings, and also some of the images extracted from the film, portrait film, some of the film as mentioned. But also we can use some cartoon images like this as training sets. As mentioned, we can create different baselines. One is we can just take the realistic talking face video. We can use a method to generate realistic talking face video and then apply some stylization like a line drawing frame by frame. Alternatively, we can apply stylization to the first frame, and then we can use warping to generate the result.
H, very common combination, and the sound is a hard K, so that the H is actually silent. For example, we have the word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
So as you can see, these are the baseline approaches. So these results are basically generated frame by frame, and therefore you get some sort of discontinuity. And these results look a bit more like warping because these are basically just a static image along with some warping on top.
H.
And alternatively, we can use generate like a realistic animation using something like a method like Make It Talk, and then we can then transfer the result using some stylization method. Alternatively, we can use keyframe-based style transfer.
Word ache containing CH, very common combination, and the sound is a hard K, so that the H is actually silent.
And I don't know when your moment was, but I bet you there was one.
Yes, as you can see, some methods clear issues with the loss of facial features. If you do frame by frame stylization, you can see quite clearly there are some sort of flickering effects.
Word.
And
okay, so I mean, there's always been a challenge of how to evaluate this kind of methods. So in this case, we use different approaches. One is we can use some metric-based evaluation. So these are based on something like based on image quality, like FID measures, to basically see how the distribution of generated and real distributions differ. So obviously for FID, the smaller is better, and our method is clearly better than alternatives. We can also measure interframe SSIM to see coherence between frames. And for this, basically, obviously you can see if you apply warping, you can get pretty good results, but our method also is very close to that. And we can also look at lip synchronization quality, and that's based on lip landmark distance. And as you can see, a few methods up here, our method basically is among the best methods. And another approach, obviously, is for user study. We recruited 57 participants, and as we can see, they are asked to rate based on naturalness, ID, person identity preservation, and lip sync, and overall. And you can see our method is favored by most participants.
When your moment was.
Okay, so these are the results generated using other different styles, as you can see.
And I don't know when your moment was, but I bet you there was one. And I don't know when your moment was, but I bet you there was one.
So you can see that we use different styles.
And I don't know when your moment was, but I bet you there was one.
Yeah, there's some issues with audio synchronization, I believe, but you can probably still see the quality of the generated videos. Okay, so these are the approach we mentioned. Now, as I said, in addition to generate videos, it's also important to edit face videos. This is because once we get the initial results, the result may not be ideal, and how can we actually edit videos so that we can get the result we hope to see. Traditionally, we obviously can use different video editing software, but these are often require expertise, and they can be quite time-consuming even to make some relatively simple changes. So the idea here is that we want to introduce some sketch-based approaches. Therefore, by introducing some small sketches overlaid on certain regions, we want to make sure the videos can be changed accordingly based on the small amount of editing. Now, this is actually a quite challenging task, because when you do the image editing, you can actually, it's quite straightforward to use a sketch. But in practice, you can see that when you have a video, the head poses and the expressions can all change. And we need to know how these edits can be propagated automatically to a range of frames which are relevant. So a few changes mentioned. If you edit one frame, this is a suitable sketch according to that frame. However, when the head pose changes, you can see the sketch action isn't aligned to the face. Semantically, that's the same editing. We want to have this mouth opening, but in practice, you can see the sketch actually doesn't work when you in the next frame or the next frame in a different frame. And you can see in many practical scenarios, if you want to apply certain operations, these certain operations can also change over time. That can be a tedious process. Some operations actually apply throughout the video. For example, if you change the eyebrows, then these will probably apply to whole video to some extent. But some others may only apply to certain time window. For example, if someone is smiling, they wouldn't keep the face, the mouth open for the entire period of time. But in practice, it's a practical smooth transition process. And it's also important to make sure the result is temporally coherent. Okay, so the key idea is we observe there are two major types of editing propagation. One is temporally consistent. So anything when you edit, it applies to the whole video. The other type of operation, like smiling, it only applies to a certain time window, so it doesn't apply to the full video. And there's basically fade out process. You can see how the mouth opens and then close. And in practice, there are also some operations applied to different areas. So we can actually combine operations applied to the eyebrows and maybe also to the mouth, and then to generate the result we want to achieve. So the basic idea is to consider from the sketch editing and temporal editing and region-aware fusion. So in our case, given an input video, we can extract the facial region as this aligned video. And then we can extract basically use diagram to help handle cases of different facial directions. So basically for this aligned video, we can extract a few frames. If we identify a certain edit direction in the W plus latent space, and then the whole idea is if we apply this edit vector to these frames, we can basically generate the similar editing effects, but applied to different poses and in different scenarios. And in this case, if we want to edit some features which are consistent, the spectra is applied consistent to all these frames. And finally, the edit video is overlaid, put back on the original to get the merged video. Okay, so the first thing is, if user draws some sketch, how do we know what editing operations should be performed? The whole idea is, first of all, we basically create an extended version of the style again, which not only generates an image, but also generates a sketch. Okay, so that's quite straightforward. You can also use a sketch as part of the target to optimize the network. And then if once you use a label some certain region and draw some sketch, then we have a loss to we basically want to update the latent code such that the generated sketch is as close as possible to the given sketch. And for pixels outside sketch, we want to keep them as stable, as unchanged as possible. And we also use that basically for a given sketch editing. We can use this approach essentially, to go back to the original latent code to work out the new latent code. And then we can use the difference between the edited latent code and the original latent code to work out the editing direction. Okay, so for temporary consistent editing, once we get this editing direction, we can basically add this direction to all the frames to get the edited results. Okay, so that's the temporal consistent result. So you can basically see the eyebrow is edited from here to this way, yeah. And alternatively, if it's temporary variant editing, what we need to do is we want to make sure only certain frames are affected. So in this case, when it smiles, it goes to the full edit direction, but then we gradually reduce that to go back to the original closed mouth. Okay, so the basic pipeline involves these different scenarios. One is if the user editing is temporal consistent editing, we basically extract the delta vector, edit vector, and apply it consistently to the whole video. If the result is not temporally consistent, coherent consistent, there are two scenarios. One is for certain operations, it only applies to a certain temporal window. Then we can use this kind of a shape of the temporal window and basically multiply that with the delta, the edit vector. So basically, only when during this time window, the edit actually increases and then drops. Alternatively, certain editing will be related to some facial expressions. For instance, we can say, okay, we want to make the mouth opening larger when someone is smiling. So that basically means this kind of editing operation only applies to certain facial expression, and we can use a basic facial expression extractor and use that to drive different combinations of editing operations. And finally, we can get to different local editing regions. These are warped towards the final the target frame, and then these are then combined to generate the final results. And this, you can see how these local editing are combined. So some temp window editing here, and like the beard is the shape editing, which is across whole image, and this hair editing. All these are actually merged, and we can then get the edited video. And this is a more close view. Okay, so some examples. This is a temporary consistent editing. So this basically changed the shape, the face shape. And you can see this is basically applied to the whole video. And this is temporary consistent, also temporary consistent editing, basically makes the nose a bit thinner. And there's a time window editing where we try to make the smile, but it's only applied to a certain time window. So it's not mouth opening, it's basically smiling. Some expression guided editing. So the eye is a bit closed, when mouth is open. Yeah. And some comparison with some alternative methods. As you can see, there's very little. We can't really find the exact same work about sketch-based visual video editing. But obviously, there are some alternatives. We can use some baseline by, say, generating a sketch sequence and then apply some frame-by-frame translation, like a few shots and vid to vid. But as you can see, the quality is still clearly worse. So you can see it's quite clearly these results are blurred and of lower quality. And it doesn't generate a proper time window editing as well. Okay, so basically for the editing side, we show for a sketch-based human portrait video editing system, and we can see that user-specified sketch edits are represented in latent editing vectors, and which is achieved through this optimization in the latent space. And we consider editing sketches as two types. One is temporally consistent, the other temporary variant. And we also consider how we can fuse results from different edits into multiple frames. So overall, basically I talk about some of recent work on how to help generate face videos or even stylized ones with reduced effort. There are still many areas for future improvements. For example, especially for some challenging cases, there are still ways we can possibly improve the quality. There are still sometimes some temporary inconsistent results, or some small artifacts. And there are also questions how we can generate more general results. For example, talking about head motion. So current approach, we basically use a simple approach where we just keep the head motion from the input video, but that may not always be the best choice for the specific audio. So when you change audio, there could be cases where we also need to change the head motion to be more realistic or more natural. Other tasks, for example, when we generate, there's no easy way to specify the change of pose with editing. So we can change the facial features, but it's quite hard to change the facial pose. So there are also issues if what happens if users edit multiple regions which actually have conflicts, and what we should do to make sure the results are still coherent. And another issue, obviously, is about how we can evaluate the results. In many cases, we can show some narrative results, but how can we prove one method is better than the other? So evaluation is still a big challenge here. Okay, thank you.
A very nice talk, and thanks a lot for Professor Yukun's talk. So I have two questions. The first question is that for the first work, could you use one person's video to drive another person's movement?
Yeah, so I probably didn't have enough time to explain how this works. So in order to achieve real-time results, basically the input is a single video of a certain person, and the audio certainly can come from somewhere else. So it doesn't need to be the same person, but the output basically will have the same identity and the pose as the input video.
Okay.
So we can use somewhere else to audio, but we retain the head pose and head motion and the identity.
Okay. So for the second work, is there a limit to the type of style?
Well, I think as it stands, it seemed to work with most styles we tried. We tried a variety of styles from watercolor to cartoon and line drawings. In some sense, line drawings are probably more difficult because usually when you use sparser elements, any artifacts will be more noticeable, right? So if you have lots of the small elements like a painting, even if it generates some artifacts, you probably won't actually even see that. with line drawing. So if the style is more abstract, like line drawing, it tends to be more difficult and more challenging because small artifacts can be more visible. So other than that, I think it should really work for most styles. Yeah.
Okay. So thanks a lot again for Professor Yuken's nice talk.
Yeah, okay.
Thanks a lot. Yeah. And also thanks a lot for to the great effort of two speakers has made, and also thanks a lot for your listening. And the webinar is completed now. Thanks a lot.
Thank you.